We'd like to welcome you all to Audio Fest, and certainly we hope you're all having a great time. My name is David Solomon. I'll be moderating this event, or mediating it, depending on how jumpy the panel gets. So we've got a really terrific panel for you. To begin with, I'm Dave Solomon. I own a company called Signal Path, and we produce a product called Peachtree Audio, the Deco, which is a little integrated amplifier with a D to A converter built into the front end, and we're very, very much into the whole digital audio and how it's being transferred, and where it's being transferred, and who it's being transferred by, and how they're doing it. And we've got just an absolute terrific panel of experts that will be answering your questions, making statements themselves, and trying to keep it on a level that most of us can understand. Just as a point of interest, how many engineers do we have in the room? Okay, so that's good, because the panel that we've got here, they're all engineers. They all really know what they're talking about, and they can get very deep in this. We had a discussion to begin with, and we all decided to try to keep this down to a level that civilians can understand. I like to call them guys civilians if you're not really deep into this. But it's something that will be meaningful, something that you can actually take away from this. It's information that you can use to research, to know where to go, to know what types of questions to ask, and then hopefully give you guys some direction on where this whole industry is headed. So first I would like to introduce Michael Goodman. He's from Centrance. Michael, he was with Shure Microphones for 10 years. And Michael was the guy that actually developed their first D to A and their A to D. So Michael's got a good bit of experience in this. He's the managing director right now, and they've got some absolute cool products mostly on the pro side. But we all know how pro products typically lend themselves to consumer products, either at the same time or a very short period of time afterwards.
The current company is called Centrance.
Yeah, right. We'd say that, I think, Centrance. So Michael's big thing is making computers sound robust enough for the pro audio. That should really, really fit well for this type of audience. He also does work right now for Mackie, Korg, Benchmarks, and he's quite the jazz bassist, we understand. So he's got a good musical background for this. Next guy I'd like to introduce is John Seow, and you guys are all very familiar with John's company. It's Benchmark, who has just done an absolute wonderful job in the pro side and the consumer side. And in fact, at the consumer side, I would credit Benchmark to getting quite a few of you guys into this, or at least get you interested in it. They got great white papers online, and John's actually an engineer for the company, and has designed quite a bit of stuff for Benchmark. I guess all of the Benchmark products now. So he's a great guy for a resource for you guys. He's done their microphone preamps, and he's also been in video production prior to this, designing PLL circuitry for HDTV, and he was in the design group for Dolby as well. So we'd like to welcome.
No, it's not Dolby, but with CBS Labs.
With CBS Labs, I'm sorry. Yeah. The next person we would like to talk to you guys about is Andy McCarg, who is with DCS. You guys are all familiar with DCS. It's probably all stuff that we aspire to own one day when we get rich. And these guys have just done a terrific job. Very, very innovative company from way back. And these guys sell probably some of the most expensive, well-known high-end digital gear ever. Andy is their software designer and has been there for, again, how long?
15 years.
15 years, so he must be pretty good, or they would have probably gotten rid of him by now. Let's see.
He has all the source code.
He's got all the source codes.
Can't get rid of him.
He's like your IT guy at work. He knows way too much for them to ever get. So Andy is the director of software. He's been there for 15 years, and he's written all of the software for DCS. So as you can see, this panel it's a fairly diverse panel with knowledge ranging far, deep, and wide. So one of the rules I'd like to set up for this, I almost want to call it a debate after the last few weeks, but one of the rules that I'd like to set up for this seminar and for this table discussion is, if you got a question, if we're talking over your heads, please raise your hand. Now, what's going to happen is one of the guys, because this is all being recorded, don't be afraid. Somebody's going to stick a microphone in your mouth and speak in the microphone, because this thing could be watched. There's no telling how many people are going to end up seeing this. So please, if you've got a question, more than likely the 80 million plus people that will see this throughout the years will have the same question. And please don't hesitate. We'd like to keep this as fun and light as possible.
You guys are going to be the next YouTube stars.
That's right, YouTube stars. Okay, what we're going to be basically going over with our panel of experts are key functions in the playback chain, critical components and problem areas. What does it all mean, and what should we be looking for when we start looking for these key components in our playback chain? We're going to be talking about transports, and that can really sort of run amok these days, from CD transports to media servers to bridges like Apple TV and Squeezebox and Sonos, those types of things. Media extenders. We'll be talking about digital receivers, upsampling and filtering, digital to analog conversion, and then finally the output stage. We're going to take all of these pretty much individually, and we're going to give the most attention to what you seem to be the most interested in. So this is for you, not for us. These guys already know all the stuff they know. So this will be basically for you. The first thing that we're going to talk about, and I'm going to hand this off to one of our panel members now. We're going to start off with John. We're going to be talking about how important clocking is in a system. What jitter is, what does it sound like? What does it do? What's its function? And how can it degrade the sound? And then we'll be talking about noise as well. So to begin with, we're just going to open this up and pass this off to John Sia from Benchmark.
Thank you. And welcome to all of you here. Glad you could come today. And please feel free to interrupt with any questions. We want this to be an interactive session. Jitter is just one of several unique things to digital audio that really separate it from analog audio. Well, there are analog equivalents to jitter, and of course, with wow and flutter, things that we're familiar with from the analog world. But what I want to emphasize is that some of the unique problems with digital audio have distortion artifacts that are very non-musical and unnatural. If you have an analog amplifier that has a little bit of distortion in it, you may get second harmonic, third harmonic distortion. But these are overtones that really occur naturally in music and are less objectionable than the artifacts that we can get from digital audio. Jitter does not give you harmonic distortion. Jitter gives you distortion artifacts that are completely non-musical. They're not anywhere near falling on the natural harmonics of the instruments. And in fact, jitter creates tones above and below the the tones of the musical instrument. If I'm playing a certain note on a musical instrument and I've got jitter at 1 kilohertz, I'm going to get a tone caused by the jitter that's 1 kilohertz above and 1 kilohertz below the tone that I'm playing on the instrument. And if you can imagine each of the tones that the instrument's playing, I mean the instrument's playing and it's rich in harmonics. Each of those harmonics also generate jitter components above and below them. So I get this whole clutter of non-musical tones that are appearing in the audio if I've got a jittery clock. And one of the things that we've done is the A to D converter that in the studio and the D to A converter that's in your home have got to have very precise clocks. Now, how precise? It's amazing how precise it has to be for digital audio to be at 24-bit performance levels. Or let me put it another way, it's amazing how accurate the clock has to be to bring the jitter to inaudible levels. If I want to get those jitter components down, say below, down 120 decibels down from the peak signal levels, I've got to have jitter that's less than 20 picoseconds. So we're talking about 20 trillionths of a second, and do I really need that for audio? And actually you can show that mathematically those are the kind of numbers you need. On these little thumb drives, I put a little thumb drive on everybody's desk, and for those of you, the 2 or 3 of you that raised your hands and said you're engineers, there's an Excel spreadsheet on there that actually allows you to calculate the level of jitter-induced sidebands based on the amount of clock jitter. And so it's just kind of one of those geeky things that kind of put on the thumb drive. But I don't know. Anybody else got some comments on? Do you want to add?
Hi, I'm Andy. I'm English, so I'm very sorry about that. I don't know if any of you are familiar with the Daleks from Doctor Who. Anybody? The effect of the Daleks is called a ring modulator, and if you had, I don't know, maybe 100 microseconds of jitter, you'd have a similar effect to the Daleks.
Yeah.
I made a Dalek ring modulator at work one day. So.
Before we get to John, I'd like to apologize to him to begin with. I didn't introduce a very important member of our panel. John Stosinger is he's managing director of. I'm just completely.
That's okay. I'm the
here.
president of Belcanto Design. And
Belcanto Design.
I assume most of you heard of the company at least.
Belcanto is, of course, a very popular company, and it's sold a whole bunch of digital stuff. John, he's responsible for all of their high-speed and digital circuits in the Belcanto, and he holds a number of patents in these areas as well. So John is absolutely qualified to be here too. And John, could you speak a little about the jitter and clocking and noise?
When we were experimenting and developing the DAC-3, I originally specified a clock that had around 25 picoseconds RMS jitter, thinking, well, that should be good enough. And we experimented with a 2 picosecond spec part, and the improvement was easily audible. So I honestly don't know where the limit to jitter is. The ear seems to be supremely sensitive, and when you reduce jitter, what you get is much greater dynamic impact, dynamic subtleties coming out in the music. You get better harmonic resolution of what the instrument's doing and how it's being played. The harmonic envelope seems to be much more realistic. It sounds more analog, quite frankly. So in my experience, jitter is, in some ways, for me, the last frontier in digital audio. If we can hammer the jitter problem, once and for all. We're all going to be a lot happier with digital audio than many people are today, especially when we think about all of the alternative sources that are coming out, high-res sources on computers, where we've got Ethernet, FireWire, USB, as well as AES EBU sources. All of those sources are forward paths for jitter. So D to A conversion, if it's ever going to transcend the best of analog, either tape or LP, is going to have to control the jitter issue, and to levels that are frighteningly low. So that's my experience with jitter.
From the pro side, I'd like to hear from Michael on jitter, and then I'd like to kind of wrap this up by with our panel discussing a couple of topics. What they feel the best method of transferring digital audio is as related to clocking and jitter, if they've got any of that stuff, and maybe a couple of questions that you guys could ask when you go in and you're talking to your local dealer, or you're blogging, or you're wanting to know what really to ask as far as, what should these numbers be, what should I be looking for. So right now, Michael.
Yeah. My perspective is more from the computer connectivity side. Our company, Centrance, has been involved in FireWire, USB, and LAN audio traffic for the last 7 or 8 years, and we've done a lot of work in driver development specifically for Windows XP and now for Windows Vista, and also Windows 7, which is going to be coming out hopefully next year. We'll see, maybe 2 years from now. But these iterations of Windows have created an opportunity for us to keep redeveloping our drivers, and sometimes it's lucrative if you're in a licensing business like we are. What we've learned is that no matter how good of a job you do in the driver space on the computer, there's still going to be a cable attached to one of the ports. That cable is going to go to some sort of a box. During the transition from the computer to the box, your audio is going to experience some degradation, be it analog, be it digital. Surprisingly so. We think that digital is just ones and zeros. Well, not really. So at the box is where really you have to make sure that the jitter gets reduced. We've done a lot of work basically ripping out the Microsoft portions, the portions of the Microsoft audio drivers for both FireWire and USB, replacing them with our own robust stacks. That's what the driver is called. And we have computers that don't crash, that are used live on stage. Cirque du Soleil, for example, uses some of our stuff, but yet at the same time, there's nothing we can do in the computer about jitter. Jitter has to be managed in the box, and some of these guys have done a tremendous job in taming it where it really has to happen, which is right before the D2A.
Michael, in your opinion, what is the best digital transfer from, say, a computer setup? Would it be FireWire or SPDIF or USB? What do you think?
It could be a loaded question. It depends on which wire you're banking all of your R&D dollars on. Fortunately for me, we're really kind of standard agnostic in our company. We're really not specifically banking on any of those formats, and we are compatible with either one of them. So hopefully I can talk without a particular prejudice. I think that FireWire, nevertheless, for years, for the last, 3 or 4 years, has been universally accepted in the pro audio community for its robustness, for the ability to reconfigure the network on the fly. In general, FireWire is a much smarter standard than USB is. It was designed for devices that were smarter than mice and keyboards. And this is why the pro audio community has pretty much embraced FireWire for all of their high channel count, high sample rate, and high bit resolution applications. However, USB is also making inroads in professional audio. USB is definitely cheaper, so you have an advantage there, especially if you're trying to make your device very cost effective if you're a manufacturer. And these days, Cat5 applications are starting to become much more prominent due to the ability of, first of all, your Cat5 cable can go a long distance, so you can wire home for a whole bunch of points of presence for your audio.
Just so you guys know, USB has an absolute limit. It can only be powered and received by, I think it's about 16 feet is about its limit.
About 50 feet.
Yeah, okay.
Yeah.
Right.
Unless you use there's a fiber optic cable you can get from Optisys that you can go up to 150, so there are ways around.
And
it,
USB both sides.
Yes, yes.
Great.
Same thing with FireWire as well. It's about 10 feet. You can get boxes that go from FireWire to optical, then from optical back to FireWire. Those boxes are expensive, and then basically that defeats the purpose of FireWire. You don't have a single cable anymore. You have at least 3 cables or even more, and a whole bunch of boxes in between, each of which, by the way, introduces additional jitter. So you have length limitations for both FireWire and USB, which were both standards developed for things that live around the computer, basically in the immediate vicinity. Anytime you start talking about computer in one room, stereo system in another room, in a typical house, where, today a lot of people are using computers as music servers. This is where all your content resides. And you don't want the computer which, has fans and makes all kinds of noise, specifically located right next to the speaker, because that's going to affect your audio quality. You're starting to think long cables, right? And this is where Cat 5 is starting to win out, simply due to its ability to carry audio long distance.
Great. John, I think, did a fantastic job of talking about the audible effects of jitter. And Michael, great job on the different transfers and whatnot. John and Andy, how do you guys do it in your company, and what advantages do you see it in the way that you guys are doing it? How do you transfer? What's your preferred method?
Well, we have either AES, EBU, SPDIF, or USB today, but I'm going to be talking with Michael later about Ethernet. I think that's the future ultimately.
Yeah, we do. Yeah. Andy?
We support AES, EBU, SPDIF, USB, FireWire. The important thing is to separate out any jitter from the interface with jitter at the DAC. You can have as much jitter as you like in the digital domain. It's only at the DAC that jitter is important. The thing to remember about jitter is that the right sample at the wrong time is the wrong sample.
Pretty much. Well said.
Thank you very much.
I think all these guys, as in their general philosophy, every single one of them reclock the signal before it ever gets to their D to A converter. So when we're talking about the companies that the panelists are involved with, they all deal with this problem. Similar, it may be a bit different, but they're all looking for the same end result, which is to get that jitter down as much as possible. And thank you. I was just about to start asking for some questions. Yes, sir. Can we get a microphone?
I may be asking your question. I don't know. How important is the cable, the quality of the cable that makes the connection?
The digital cable.
Correct. Let's say between.
Today, it's maddeningly important.
Well, you hear both sides, because you hear, well, it's just digital and a cable's a cable.
No, it's not. I mean, we're talking about analog errors here. Clock edge placement is really an analog error to low-level clock edge placement. And I wish I could say the cable doesn't matter, because that means my DAC is extremely robust against jitter coming in. But honestly, it still matters, unfortunately. I don't know if that's John's experience.
Yeah, actually, I have a different opinion on that. We do tell customers that the cable is irrelevant when using our box. We have a number of charts and graphs in the back of our manual where we've run a number of tests on that, including running the digital audio through 1,000 feet of cable before it gets to the D to A converter. One thing I think we will all agree on is that we have to reclock the data before it goes into the D to A converter. And Andy, thank you for bringing up that point, that what really matters is the clock at the D to A converter. Up until that point, all we're worried about is getting the ones and zeros from box A to box B. But what's important is that we clock those out at exactly the right interval in time.
Yeah, I want to mention I've done the same measurements that John mentioned, and I cannot honestly measure what my ears are telling me on our instruments. Unfortunately, the ear is more sensitive than static measurements seem to show. But give it a try. Don't assume that a cable is just a cable.
Maybe to put it in a slightly different perspective, the worse the cable, the harder the box has to work to get it back to normal. Just a very simple explanation.
Andy, do you have anything to add to that?
I'd say the right cable is not necessarily the most expensive cable, as long as it's correctly terminated. That's the key thing. I mean, it's a high frequency signal, so the termination is vital. But you shouldn't have to pay $1,000 for a cable.
Yeah, in our experience, it's been very similar. We do USB, a lot of USB conversion, and we've used some very expensive cable and some fairly inexpensive cable. And to my ears, once you've got the ones and zeros to where they're going, you've kind of got it. So we're opposed to the $10,000 cable as well. Yes, sir.
There's somebody with a
Oh, I'm sorry. No, go ahead.
Were you?
Yeah.
Yeah.
Well, what I wanted to ask was whether there's an agreement on how to measure jitter and whether there's a standard test, because I've done some research and it seems like there's no agreement. Second, we have a legacy of jitter measurements from like stereophile, for example, and it seems like jitter's going down, not necessarily because technology has improved, it's just they're measuring it differently. So, part of your point was, you want information from the consumer to go into their store and ask, and you guys are all making things and publishing jitter, and some making claims that their technology removes jitter, and then it still comes down to, well, you listen and you can hear it. So just interested in comments on, one, how do you measure jitter? Are you all in agreement? You're measuring the same thing? And 3, is the final source our ear to say?
Comments on that. There is a great application note, and I use the word application note kind of lightly because it was written by Julian Dunn, and Julian Dunn unfortunately has passed away a couple of years ago. But this application note is really a book. It's about I don't think it's about 100 pages or something, and it's available from Audio Precision. You can download it, and it is a wonderful manual about how to measure jitter, how to understand jitter, what jitter is, and one of the methods that he talks about is measuring jitter performance with an FFT analysis of the output of the converter, and with an FFT we can look 150 decibels down into the noise or down below full scale, and really see these jitter components that contribute to the audibility of jitter.
You guys want to comment on how you?
I'd say that the jitter is extraordinarily hard to measure, and the spectrum of it is as important as how big it is, and so these 200 picosecond figures are pulled out the air as far as I can tell, and so I'd never go and say how much jitter has it got, because saying 200 picoseconds, 300 picoseconds, it doesn't tell you the spectrum, doesn't tell you anything about it. At the end of the day, you have to believe in the topology of your manufacturer that you're dealing with, and try not to buy into all the snake oil that goes around, and let your ears be the judge of a component. Never ever buy anything on measurement.
Well put.
Or on spec, on a published spec.
Right. I would agree with that. And one thing to remember is, I know we use similar techniques for really jitter attenuation. There is no, using serial interfaces, meaning the interfaces we've been talking about here, clock does have to be recovered out of the data. And the best that we're doing today is to attenuate the jitter. And where the technology's really gotten better is the attenuation. If the old, not to pick on Cirrus, but they're used a lot, the old analog phase lock loop-based systems, you can easily measure the forward jitter using the FFT approach. cascading that type of a phase lock loop with these new asynchronous sample rate converters with a digital phase lock loop in them basically gives you 50 to 60 decibels better attenuation or more and at much lower frequencies. So we are indeed attenuating much more jitter in today's designs. I think the next step is going to be finding architectures and techniques that are not, where there's no forward sensitivity in the serial data path to jitter influencing the clock. And how the clock actually, we use similar techniques. The clock itself is not even it's just an oscillator sitting next to the DAC, basically. So theoretically, it should be the perfect thing. But these asynchronous sample rate converters basically take jitter components and take them out of the time domain and put them back into the amplitude domain in the resampled points on the output. So while they certainly work to improve things, today there is not a final solution for jitter, I would say. That's my personal opinion on the subject.
So,
Kurt's got, I'm sorry.
Yep.
Why don't you go? Okay.
so I certainly agree that you will have jitter. So you have to you have to somehow attenuate it, do some jitter rejection, whatever you want to call it. So I would claim that you should have a disk somewhere on your network, and then do Ethernet, and then have some. I'm throwing a little bit oil into the fire, perhaps, but. And then do some kind of very specific reclocking or buffering or whatever scheme at that moment in order to, because anything leading up to it is going to have jitter, right? And SPDIF is particularly bad, right? You have to recover clock from the signal, which is about as insane as it gets when you're thinking from an engineering point of view. So what I'm curious to hear from you is whether you have any sort of, let's say, favorite or favored approaches to the jitter rejection in the box itself, right? There's basic engineering things. You know, you have to have a good oscillator. You want to have it extremely close trace to the DAC itself. You know, layout. There's various sorts of. But then there's questions such as: do you do rebuffering? Do you do retiming? Do you do? I don't know. There may be more exotic things. So I'd be curious to hear some thoughts on what you do inside the box to do the best jitter rejection or attenuation, or whatever your favorite term for it is.
Yeah, we need to probably keep that one down to about a minute apiece, no longer, because we're starting to run out of a little bit of time.
I would say that we've got two guys here who use the asynchronous rate converters to that basically decorrelate. Well, they turn jitter into noise effectively. At DCS, we don't believe in those because we don't like them for many reasons. I don't want to get into a fight. So at DCS we believe that you solve the problem of jitter. You don't just at the source. And so our USB solution, it's a buffer. We tell the PC how fast or slow to go. Any jitter is on the input to the buffer. The output of the buffer is clean. We sell a clock that's separate from any mechanical or server type things, and so because we have a separate clock and transport and DAC, you can arrange it so you can derive the clock from the SPDIF. You can derive the clock from a word clock, which is got no data components in it. You can run the DAC as the master, and so the DAC then controls the server in the transport. And so we remove the relationship between the data transport and the clock transport. So they're completely separate. They can't influence each other.
I would agree with that approach if money was no object.
So if money is an object,
then you have to take other approaches. But anyway.
I've actually got products that use both of those approaches. Our earlier A to D and D to A converters used two-stage phase lock loops with a corner frequency of 1 hertz. And what that means is that jitter frequencies above 1 hertz would begin to be attenuated. Jitter frequencies below 1 hertz were not attenuated. And the lower you can push that corner frequency, the more jitter you can attenuate. And higher frequency jitter is certainly more audible than low frequency jitter. But the problem is that a lot of digital audio receiver chips that are made have corner frequencies at 5 kilohertz and 7 kilohertz. And so that whole region between the 1 hertz corner frequency, and I think, Andy, you've probably got corner frequency that's down in that range as well.
Yeah, we don't use any digital receiver chips. It's all handcrafted.
Oh, that's right. You're sending the clock the other direction, so you don't have to do the phase lock loop thing.
Well, we have the capability of using a phase loop, and that's all designed in-house.
Yeah.
In an FPGA, it's a hybrid digital analog PLL.
But the sample rate converter we use also has a 1 hertz corner frequency, and at 1 kilohertz it has 110 dB of jitter attenuation. So you get this very steep roll-off of jitter, and it does actually attenuate it.
A good old PLL will do a good job, and also making sure that you clock it. This is what we do on the computer side to clean things up. Have a buffer. The length of the buffer really determines how robust the system will perform, especially in a computer. And then it doesn't really matter how jittery it comes in, as long as it's clocked properly on the outside, then you're in good shape.
Yes, we have one more question up here. And then we're going to move on right after this.
Yes, thank you. I was wondering how critical is the power supply for your DAC?
We're going to get into power supply.
For jitter and the
We're going to get into that, actually. It's going to be a separate topic.
Okay,
Thanks for asking. The next critical issue down the chain that we're going to be talking about is going to be digital filtering and the conversion architecture of these different companies. And I'm going to ask the panelists to try to lighten up just about 3 dB so that we can sort of meet the meet the level of knowledge of the audience. And if we can give some examples with when you guys are talking about maybe products that you've got that do what you're talking about, so these guys can go out and actually listen to it and see if they can hear it. I think that might be helpful as well. So we're going to go ahead and turn this one over. I think I'd like to start on the pro side. This time, Michael, we'll let you start off with the digital filtering, and then we're going to go high to low. We'll start with Andy and go to John, and then to John. Okay.
Yeah, I'll be brief on that. We believe, especially on the quality audio side, that filtering is not necessary. Having said that, I've done a lot of work on the pro side with filters that are designed to enhance the sound. Right? I've done work for processors, consoles, etc., things that record the audio on the professional audio side. There, of course, there's a whole bunch of filtering mechanisms and algorithms that you can use. We'll probably get into oversampling in just a moment, whether that's a good thing or not. Once again, just to sort of put things in perspective, on the pro side, you don't always have the need for absolute pristine audio because you're actually creating the audio yourself, and it's under your fingertips. And you don't have this utmost responsibility for preservation and pristine recreation of whatever has been recorded by somebody else. When you do have the flexibility of creating the audio yourself, you're less concerned about the quality and you're more concerned about the artistic expression. And that's why you don't really see too many $20,000 ADCs or DACs on the pro side, because people are content with stuff that's $100, $200, especially in the project studios these days. We can talk about how much our world has changed, but at the same time, it's also given a whole bunch of people an opportunity to get into audio production on a budget. So as far as filtering is concerned, I'm probably going to step back and not take the purist approach on this and let these guys duke it out. So go.
Andy, how do you guys handle digital filtering?
Probably the first place to start is to understand why you need filtering. When you sample something, every sample that you take, that sample can represent an infinite number of frequencies that are related to the sampling rate and the and the signal you're sampling. So if you sample a 20 kilohertz signal at 44.1, if you were to just present those samples back to a DAC with no filtering, you'd get out an image at 24 kilohertz and at, well, loads of frequencies after that. And so the key to filtering, and this is where 44.1 was chosen, and it's actually the hardest filtering to do is at 44.1, because you only have a 2 kilohertz transition band, and a transition band is where your filter will have a flat response up to your transition band, and then it has to attenuate very quickly, and you only have 2 kilohertz at 44.1 to attenuate, and that's not a trivial task, and that's why analog filtering can't do it. The first CD players had a very expensive set of filters that were not phase linear. The first set of CD players sounded awful because of this, and so oversampling means that your analog filtering is done at hundreds of kilohertz rather than at 20 kilohertz. The problem with filtering that you do have is that the steeper your filter, the more coefficients you have, or the more taps in your filter. And because everybody's an FIR filter, which is the only way you can get phase linear responses, you have a pre-ringing effect. Depending on the material, depending on the system, that pre-ringing may or may not be a good or a bad thing. So at DCS we offer a software selectable set of 4 filters, and so the steepest one is, I think, 130 dB down at 22 kilohertz, and the softest one is 6 dB down at 22 kilohertz, and it's up to the user as to how it sounds in their system, how they feel, the material they're playing, and this is where higher sample rates really help, because you can start rolling off at 20k and then have a really lax filter, and that's really easy to do.
John?
Yeah, in our designs, that's pretty much the approach we take. I like to run the final D to A conversion at the highest rate possible, so that the digital filter is far away from the audible band, and then we also use a slow roll-off filter, which sounds better. It sounds more natural. That's another reason to use the sample rate conversion, is to get those digital filters as far outside of the audio band as possible. They're a necessary evil, I guess.
John?
Yeah, we upsample 44.1 kilohertz, actually upsample it to 110 kilohertz. And the reason for doing that is to avoid a lot of the problems that occur in a 44.1 kilohertz filter. It is very difficult to build a good filter that sounds good, that's so close to the audio band that we're trying to preserve. And so by upsampling, and we do it asynchronously up to 110 kilohertz, we're even able to move that transition band of the filter that's actually in the DAC. We're able to move that above any audio content that's going to be in a 44.1 kilohertz stream, a 48 kilohertz stream, or even a 96 kilohertz stream. So at 96 kilohertz, we still upsample to 110 kilohertz, so that the low-pass filter in the DAC chip is above that, above any frequencies of the audio in the digital stream.
One more thing that wasn't spoken about, I'd like to jump in and add. We've talked about oversampling and the frequency at which your filter runs. We really haven't touched upon the bit width on which your filter runs. And in the computer domain, where we do most of the work, it is actually easier because it's 32-bit, right? And then so a 16-bit signal that comes in, or a 20-bit signal that comes in, can actually be processed at 32, or now these days 56 and even 64 bits, where your dynamic range is pretty much unlimited. And the noise floor of the filter and all